All good.
So let me briefly, I don't know if everybody is aware who's Diamond, but just for a very quick introduction of the company. The company is a privately owned company with more than 60 years experience. Headquarters is located in Switzerland, in the southern part of Switzerland, and we are specialists in manufacturing of ultra-high performance fiber optic connector and assembly as well, fiber optic assembly, working in very tight tolerances. We have in-house manufacturing of our product at more than 90% of internal production, and we can also offer ISO 5 and ISO 6 clean room capability with a manufacturing floor up to 800 square meter. We are globally, we have 60,000 square meter located mainly in Switzerland and 2 other sites in Germany and the US with different qualifications, specifically ESA in Switzerland at HITAR in the US. The main topics of today is in regard of ultra low loss interconnects. What we experienced, let's switch over. What we experienced is that in the last, let's say, 2-3 years, we were quite continuously challenged to develop solution for low loss connectivities to serve quantum application in different of different types, let's say quantum computing, cryptography, and communication as well. And over these different requests, we started development activities in order to get optimization for transmission of individual photons over optical networks. And this led us to develop a new class of connector, namely ultra low loss, that we are now, I want now to show you some more in detail. As per our understanding, what is ultra low loss means is a connector that is capable to grant losses or extremely limited losses up to the level which is really comparable with measuring uncertainty. And that's what we are dealing with at the moment, doing, let's say, making use of the basics of fiber optic transmission. Those 2 parameters that we are now showing on this slide are the main driving factors in order to get poor or very high performance connectivity in fiber optic. And as you can see, out of ferro properties, which can be listed as diameter, shape, and hole diameter and whatever, what is very, very important for a high precision connectivity are lateral and angular misalignment of the fiber core itself. So in order to get rid of lateral misalignment, Diamond has developed many years ago their own technology, which basically are constituted over this statement, which is showing that even in the IEC international standard, there is a definition of attenuation for fiber optic connectors, which is basically done by having eccentricity and angular misalignment under control. Those 2 parameters are leading to different categories of connectors, and what we can see that is that typically with state-of-the-art single-mode fiber and high-precision ferrules, which are available nowadays on the market, we have to handle with still a maximum 1.5 micrometer eccentricity. This would mean that even by having the perfect components in place, you have to, or you may be affected by an intrinsic loss up to 0.2, 0.3 dBs. In that case, our focus was to work on eccentricity, and we started, or the basics of our technology is at first level using the composite ferrule, which is also defined by the international standard. Under composite ferrule, you have to understand a ferrule which is built using a hard zirconia ceramic sleeve, very precise machine in a scale of tenths of micron of precision, combined with a ductile titanium insert, which serves as a guiding element for the optical fiber. Using this ferrule, Diamond offer active core alignment technology, which basically has a target of granting fiber core positioning in an active way in order to get at the end of the operation less than 0.125 micrometers eccentricity. This is the base of our technology, which led appear the 0.1 dB class connectors more than 20 years ago. Now, the need of improving that technology or having lower losses in the connectors led us to start further activities still based on active core alignment, but limiting once again manufacturing tolerances, taking advantage of the latest advance in an imaging system, introducing new alignment, proprietary alignment softwares, and employing application-specific working parameters, which means that all the connectors which are named as ULL, also ultra-low loss connectors, has to be, say, developed and made according to the application-specific parameters, allowing the maximum reduction of any uncertainty. We are now, as project activity, facing to different prototyping stages and characterization ongoing in order to get a clear assessment of the influence of the type of fiber onto the achievable EL values, influence of wavelengths toward the attainable absolute values, and influence induced by the used components. All these things are now subject to further analysis, but on first results, you can see that using single mode fibers at 1550 nanometers, we had we produced a batch of connectors that provide us this distribution, having a maximum of 0.07 dB at 95% of the distribution. This was an impressive result that has been additionally confirmed by measurement performed at the US National Institute of Standard and Technology, NIST, which are working with us on this new development. In parallel, we also perform the same job with a single mode fiber at 780 to have an overview about short wavelengths applications. And as you can see, we also have a very good results showing 0.1 dB at 95% with a mean value on an average at 0.057, which compared to standard available product at 780 nanometer show more or less a reduction that is less than a half of typical values that you can find on the market. Additionally, we have performed testing using other fiber types, still at 1550, in order to get the feeling or an assessment about the behavior of different fiber at the same wavelength. And you can see that using other fiber, the values can be massively reduced. And this is what we are now managing, knowing the kind of, let's say, table frame where we can see different wavelengths, different fiber types, and corresponding different achievable values. This is for us the best way to serve any connectivity, let's say connectivity issue or connectivity use within quantum photonics in general, because as we got from our customers, it's extremely critical that any loss should be avoided. The measurement technology relying on that is measurement technologies which is well known and internationally defined. So we didn't get a new specific method or something crazy to get those results on table. It's clear that we are dealing in a level of insertion loss that is typically covered by the measurement uncertainty, and in that case, it's important to have a good selection of the material you are dealing with, the fiber you are dealing with, and everything has to be adjusted, if possible, to the parameters that rely to the application. Doing these, we can achieve the expected value by ultra low loss, and also fix the parameter belonging to the process. Because at the early stage, as we are now with the characterization of different fiber and different wavelengths, we have to perform a large measurement campaign, building histograms in order to get a picture of the quality of the results of the process. And then working with the process parameter, we grant that the overall quality of the connector are given. Ongoing projects is concrete, is not theory, is something that we are dealing with. We have already a lot of customers that they are at early trial stage with within several projects, where the connector and fiber optic assemblies, because it's not only the connector alone, but typical for that kind of application, we are also dealing with vacuum feed-throughs and low temperature connector assemblies, so that all the activities are also inspected under specific pressure and temperature conditions. And then, as mentioned before, we have an activity ongoing in order to have a kind of standardization of these connector families, working with the NIST. NIST also perform themselves measurements, and as you can see at the same batch that by us was 0.07, this is a mistake in the numbers, 0.074, here is 0.077, as you can see from the plot of the histogram. So what we expect with the ultra low loss connector serving quantum application is to ensure integrity and reliability of the quantum states, let's say, minimize loss and noise to help maintain coherence, increase efficiency of quantum communication system, and so on. So you can see those are our estimates in terms of features that could serve the quantum industry. We have also a commitment to ULL in terms of really establishing a new standard in regard to ultra-low loss connectivities. And that's it.